Previously, we studied this circuit using mesh analysis, and after applying KVL to the two meshes, we got two equations in IA and IB, and those two equations are given here again. So we had 3IA minus 2IB equal to 5, and the other equation was 2IA minus 5IB equals to 3. So these were the two equations that we had last time. And we solved these equations by finding one variable from one equation, then plugging that value in the other equation, and therefore we were able to find IA and IB. Now here we want to see a different method where we can find these values relatively easy. And that method is the method of using matrices. So the objective here is now to convert these equations or write these equations in a matrix form. And let me do it first, and then we can see how we go about that. So I will create this first matrix A, which is based on the coefficients of the variables. So it is 3, -2, 2, -5. And this is the variable, this column vector we are going to have. It's called x because this is the variable that we want to find. And on the right hand side, we have the constants, which are in this case 5 and 3. So now you see this matrix, if you multiply the matrices and equate left and right hand sides, you will get two equations, and those two equations are exactly the same as what we have above. So this is how we will write a system of simultaneous equations in the form of matrices. Now, the first matrix, we call it typically by the name A. The second one is called X, and the one on the right is called B. So this is how we write it in the matrix form AX equals to B. And we know that if we want to find X, what I can do is that I can multiply both sides by the inverse of A. So that will give me X equals to A inverse times B. And this equation, we can solve it either using a calculator, or you can solve it using any other software. So I have done this for these two equations using MATLAB, and the value of x is 1.727, and the other one is 0.0909. And we know that this means the first element is IA, which is 1.727, and the second element is IB, which will be 0.0909. So this will give us the two currents, and these are the exact values that we got previously. So you see, this is a much simpler and a much faster process to solve simultaneous equations. This method is very useful when we have more than two meshes. And in that case, I want to show as an example, if I have the following circuit. So we have, in this case, we are going to have three different meshes, and maybe something like this. All right, so we have a source voltage of 10 volts, for example. In this case, I have R1 equals to 1 ohm, R2, so this one is R2, maybe I'll write it here, R2, which is equal to 2 ohms. This one is R3, and let it be 3 ohms. And this one is R4, which is 4 ohms, and R5 is 5 ohms. So in this circuit, we have three different meshes. Therefore, we will assume three different mesh currents. This is IA, and in this mesh, I have a current IB, and over here, I have a current IC. And I'm sticking to this convention that I will always choose my mesh currents to be clockwise. Okay, with these assignments of the mesh currents, now we can apply KVL to each loop. Applying KVL to the first loop, KVL to, let's say, mesh A. For me to be able to apply KVL to mesh A, I need to assign the voltage polarities to the two resistors that are involved. In this case, the current in R1 is flowing from left to right, so I will have positive here, negative here, because current flows from higher voltage to lower voltage. I want to assign a polarity to V2. We have discussed this in our previous lecture, that V2 can be assigned in different ways. However, there is no right or wrong. You can choose either way. And the method I like to use is that if I'm in mesh A, I will assume that IA is the largest current. So therefore, if IA is the largest current, then the current in R2, we have two currents flowing in R2. IA is going downwards, IB is going upward, but IA is larger than IB. Therefore, the net current is going downwards. So if the net current is going downwards, then this point should be higher voltage and this point should be lower voltage. Okay, so this is the voltage assignments for my mesh 1. Now let's go to mesh B and assign the polarities. When I'm in mesh B, I will assume that IB is the largest current. The easiest one to assign is R3. So the voltage across R3 is V3. And we can see that the current in R3 is just IB, which is flowing downwards. So this is positive and this is negative. Now the current in R4, there are two currents, IB and IC. And because I'm in mesh B, I'm assuming IB is the largest current. So therefore, the net current is flowing from right to left, which means I have a positive here and a negative here. And we will call this V4, the voltage across resistor 4. And finally, the voltage across resistor 2 would be based on two currents, IB and IA, but IB is larger now. So therefore, the voltage on the bottom side would be plus and negative over here. And this would be V2. Now, based on this method, where I assume that the current of a mesh is largest, in which mesh I'm applying the KVL. So V2 gets two different polarities, as you can see. In mesh 1, it has one polarity. In mesh 2, it has the other polarity. And that is happening because in mesh 1, I'm assuming IA is larger, but in mesh 2, I'm assuming IB is larger. But this method, once you do it a few times and you become comfortable with it, then there is very little chance you can make errors. All right, so now finally, let's move to mesh number C, where the current is IC. So now the voltage across R4 is based on two currents, IC and IB, but IC is larger, so therefore this would be larger, higher voltage side, and this would be the lower voltage side, and the voltage across this is V4 for this mesh, so I'm going to write it here maybe. And the voltage across R5 is simple because there is only one current, so this must be higher and this must be lower, and this is V5. So now we have assigned all the voltages, so now we can use KVL, or we can apply KVL. So to mesh A, when I apply KVL, I would say voltage rise is equal to voltage drop. That's just the statement of the KVL. The voltage rise, I will go clockwise. So I will always stick to this convention that in each loop, I will go clockwise. I will choose a point over here, and from this point, I will go clockwise and come back to the same point. So when I go clockwise from point A, I see a voltage rise of 10 volts. This should be equal to the voltage drop of V1 across resistor R1. So this is equal to V1 plus a voltage drop of V2. All right, so this is our KVL. Now the next step is to convert these voltages to currents, because we want equations in the form of currents, IA, IB, IC, so that we can then solve these equations to find the currents. So V1 is simple. V1 by Ohm's law is the product of the current and resistance, so it is IA times R1. So this is IA times R1. And now V2 for me, it's a voltage drop. Remember, I'm going to assume this polarity. And now I'm saying that this is a voltage drop. And the current, net current in this resistor R2 is IA minus IB, correct? So that is IA minus IB. Please see one of my previous lecture on mesh analysis to understand why do we choose IA minus IB instead of IB minus IA. So this is now the correct difference between the two currents, and that multiplied by R2 is actually V2. So now let's simplify this a little further. We have 10 equals to R1 is 1 ohm, so I have IA, plus R2 is 2 ohms, so I have 2IA minus 2IB. And therefore, this equation can be now written as 3IA minus 2IB equals to 10. This is my first equation from mesh 1. One thing that you should notice is that there is no IC in this equation. And the reason for that is that we don't have a resistor over here. Because if we had a resistor over here, then we would have a voltage term that would involve IA and IC together, and therefore we would have a coupling between these two. But because we don't have a resistor over there, therefore the equation 1 does not have IC. Now let's apply KVL to mesh B. KVL, mesh B. If we do this, let's choose a point from where I will start and I will move around. I'm going to choose a point over here. And if I go clockwise, I see a voltage drop. Now remember, I'm going to use this polarity because I'm assuming IB is larger than IA. So I see a voltage drop V2, then I see a voltage drop V3, and then I see a voltage drop V4. So all three voltages are a voltage drop and there is no voltage rise. So therefore, KVL will say that rise is equal to drop, which means 0 equals to V2 plus V3 plus V4. And you can see that it's V2 plus V3 plus V4. These are the three drops that we have. Now V2 is dependent on IB and IA. So therefore I'm going to write V2 as a current, which is now IB minus IA times R2 plus V3. V3 involves only one current, which is IB times R3. So that is IB times R3. And finally V4. V4 has two currents involved, IB and IC. So V4 must be IB minus IC times R4. And you see this subtraction of the currents work because IB is larger than IC. Therefore, the net current is in the same direction as IB. So therefore, I have to use this subtraction instead of IC minus IB. All right, so now let's simplify this a little bit. We have negative 2IA because R2 has a value of 2 ohms. Then we have R2IB, R3IB, and R4IB. So we have 2, 3, and 4. So we have 9 IB. And finally, we have negative 4 IC. All right. So now this equation is almost there. So I will write it as multiplied by negative 1 on both sides. I will have 2 IA minus 9 IB plus 4 IC equals to 0. So I multiplied by negative 1 on both sides, and then I switched left and right hand sides. This is my equation number 2. And here you see I have all the three terms, IA, IB, and IC. And the reason is that you see IA is because of this resistor, okay, because we have a coupling between IB and IA. And IC is because of this resistor, R4. So that gives us all the three terms. Finally, applying KVL to mesh C. Applying KVL to mesh C, I will choose a point. Let's say I choose this point and I will go clockwise. So I see a voltage drop of V4, then a voltage drop of V5, and there is no voltage rise. So therefore, rise is equal to drop, and rise is 0. Drops are V4 plus V5. V4 in this mesh is now dependent on IC and IB. And based looking at this polarity that I have assigned to V4, where the positive is on the left, we see that IC is larger than IB because that's the only way we can have a positive sign on the left if IC is larger than IB. So therefore, I would say the voltage V4 is now the product of IC minus IB because the net current has to be in the direction of IC. So it is IC minus IB times R4. So this is IC minus IB times R4, which is 4 ohms, plus V5 is equal to IC times R5. So that is IC times R5, which is 5 ohms. Therefore, I will get negative 4 IB and positive 9 IC equals to 0. So this is my third equation. So let me write it in this way. Negative 4 IB plus 9 IC equals to 0. And this is my third equation. So now I have three equations and three unknowns. The three unknowns are IA, IB, and IC. So we want to now solve these three equations using matrices. So the first task is to write these three equations in the form of matrices. So I will create this one matrix A, and I will have this matrix of the variables IA, IB, and IC. And that should be equal to the constant terms on the right. The first equation was 3IA minus 2IB plus 0 IC. So there is no IC, so we have to have 0 IC. So it's 3 and minus 2. So I would have 3 minus 2 and 0. So that's my first equation. The second equation is 2, -9, and plus 4. 2, -9, and plus 4. And the third equation is 0, -4, and 9. 0, -4, and 9. The constants on the right-hand sides are from equation 1. I have 10. Equation 2 is 0, and equation 3 is 0 as well. So I have 10, 0, 0. Now this matrix is A, this column vector is X, and this column vector is B. Therefore, X equals to A inverse times B. And when you solve it, you will get X equals to 4.1, 1.1, and 0.5. This means IA will be equal to 4.1 ampere, IB is equal to 1.1 ampere, and IC equals to 0.5 ampere. So we got the three mesh currents. Once we have the three mesh currents, now we can go back and find the currents in each resistor, because the current in each resistor might be different. You see, the actual current in a resistor might be different than the mesh currents. So for R1, the current in R1 is this current, I1, and we see that this current is equal to IA. So therefore, we don't need to do anything over here. We know the value of IA, which is 4.1 ampere. The current in resistor R3 is this current. Let's call it I3. And I3 is equal to IB. So therefore, the current in this resistor R3 is actually 1.1 ampere. The current in resistor R2 is shown over here with this arrow. This is the current in R2. And this current will depend on IA and IB. I have shown the direction of this current to be flowing downwards because I know that IA is 4.1 ampere, where IB is only 1.1 ampere. So we have 4.1 ampere in this resistor going down. Okay, so this is the IA term. And we have IB, which is equal to 1.1 ampere, and that is going upwards. So the net current in this resistor, which is R2, this is resistor R2, the net current is 4.1 going down, 1.1 going up. So the net current is actually a current which is 4.1 down minus 1.1. So that is actually 3 amperes. So 3 amperes is the value of I2. And this is my I2. So now you can see that the actual current in this resistor is going downwards. It has a value of 3 ampere. And now when we know this current value, 3 ampere, which is going downwards, now we can find the voltage across this resistor. So if I have a resistor with a resistance value of 2 ohms and a current of 3 ampere is flowing downwards, then the voltage drop across this resistor will be current times resistance, so which will be 6 volt. So therefore, the correct polarity of V2 is the one that is shown in mesh A actually, not in mesh B, and it is equal to 6 volts. And in a similar way, you can find the rest of the currents and the rest of the voltages, and therefore the mesh analysis can give you all the variables that we are looking for. With that, I want to discuss a couple of more things about mesh analysis. The first item that I want to discuss is that sometimes we have a constant current source in our circuit, and we want to see how can we apply mesh analysis to that circuit. So for example, if I have a circuit that looks like this, let's say, but here I have a current source. And let's say the current source is such that the current is going upward, and let's say this current is IS, and let's give it a value of, let's say, 3 ampere. This is my voltage source, Vs, and let's say that is 10 volts. I have a resistor R1, R3, and R2. So if we try to solve this circuit using mesh analysis, we will assign two mesh currents, IA and IB. Now, if I have two meshes, this means I will have two mesh currents, IA and IB. And if I have two mesh currents, these are my two unknowns that I want to find, I will need two equations to solve this. Now, the first equation is very simple to get, which is from mesh A. From mesh A, when we apply KVL, we will assign the voltage polarities like this, and I will have the voltage rise equals to voltage drop. So I will have 10 equals to V1 plus V2. This is V1, this is V2. And V1 is simply IA times R1, and V2 is IA minus IB times R2. So we got this equation, and we can solve it, we can simplify it, and that's fine. This will give me the first equation. Now the problem arises when we try to get the second equation. To get the second equation, I need to find the voltages around this loop. I will assign this polarity now because this is my V2 based on the assumption that I2 is larger than I1. So this would be V2 and this would be V3, but I don't know the voltage from this point to this point because this is a constant current source. The function of a constant current source, as the name implies, that it will give us a constant current of 3 amperes in this case. If the circuit resistance is large, this source will produce a high voltage so that it can maintain 3 ampere. So you see the voltage that this source will produce depends on the rest of the circuit. So we cannot tell how much this voltage will be. So therefore, we cannot get the second equation. However, we actually do not need a second equation in this case because if you see, IB is equal to the source current, but in the opposite direction. Because this is just one branch, there is only one current, mesh current, and I can see that IB has the same magnitude as the source current, but just in the opposite direction. So I can say IB is negative 3 amperes. So this is actually my second equation. Or you can say that now because we know the value of IB, so therefore IB is not a variable, it's not an unknown. So therefore in equation 1, the only unknown is IA. So now we have one unknown and one equation and we can easily solve it. So that's the first thing that I wanted to discuss. The second is that imagine if this current source is not on the boundary. You see here it is this mesh, this current source is present in one mesh only. What will we do if this was in between two meshes? All right, so let's see that example. So we have the same circuit, but now the current source is here. 10 volts, R1, this is R2, and this is R3. I have mesh current IA and a mesh current IB. All right. Now the current source is IS, and let's say that is equal to 3 ampere. If I want to apply KVL to mesh A, to mesh A, I know the voltage of the source, so I know this voltage, and I can get V1 and I can get V2, but I don't know the voltage from here to here. So that will cause a problem. To get around this problem, let's see. KVL says that if you start from a point and then come back to that point, the voltage at that point will be the same. It's not going to change. Therefore, the voltage rise and the voltage drop has to be equal. All right. Now we can see that now. When I go around this loop, let's say from point A, I go to point B, it's a voltage rise. Then I go to point C, it's a voltage drop. Then I go to point D, it's a voltage drop. And then from D to E, I don't know the voltage. So therefore, that represents a problem. But let's consider this. I'm going from point C to, let's say, point F, and then from point F to point G, and G to E back. Now you see the voltage at point A, point E, and point G is the same because they are connected together by a copper wire, and there is no voltage drop across a copper wire, so all these 3 points are at the same voltage. Okay. The voltage at point C will be different, and what I want to do is to apply KVL, for which I need to find the voltage from C to E. I need to know how much voltage drop or voltage rise that will be so that I can put that in my KVL. But this path from C to D and D to E is not doable. We cannot do that. We cannot find the voltage. So therefore, an alternative would be I can go from C to F. There is no voltage drop. They are the same point. And then from F to G. So you see the voltage drop from F to G would be the same as C to E, right? It would be the same. You can think of it as the points C and F, they are, let's say, the second floor of a building. All right, they are the second floor. E and G are, let's say, the ground floor. Okay, so you can go from the second floor to the ground floor using 2 different paths or 2 different stairways. But when you go from the second to the ground floor, the change in height is the same, correct? So therefore, the change in voltage here is the same because it is very similar to the gravity examples that we have previously considered. So instead of going from C to E directly, I will actually take the other path and apply KVL. Okay, so for me to be able to do this, I will redraw the circuit a little bit cleaner this time, hopefully. This is a source current, and let's say that is equal to 3 ampere. I have IA over here and IB over here. And let's apply now KVL to this path. So we will go in this path. I will go clockwise and I will apply KVL to this path instead of the middle path because I want to avoid the constant current source. If this is 10 volts, this is V1 across a resistor R1. This is V2 across resistor R2, but we will not be using this. This is V3 across the resistor R3. Okay, so if I apply KVL to the dashed path, then I will say rise is equal to drop. Rise, let's start from here, let's say a point over here. And this is my point A. So when I go from here clockwise, I see a voltage rise of the source, and that is equal to 10 volts. So 10 is equal to V1 plus V3. All right, now we need to pay attention to this point. The voltage V1 is the product of the current and resistor. The current is IA and the resistor is R1. Okay, now you see I have used IA over here because this resistor is in the mesh where the current is IA. For V3, V3 is the product of current and resistance. The current is IB and the resistance is R3. Okay, so you see I have to use a different current because in mesh B, my mesh current is IB. And you can ask yourself that why did we have to do this? Why do I need different currents for the two resistors? Because we are now considering the outer loop. Why can't we assign a single mesh current to the big loop instead of the mesh currents that we have? We cannot do this because of the following reason. Let's say I assign one current. So that will say that the current that is flowing over here must be the same as the current that is flowing over here. Because if I say this is I, let's say if I say this is IC, then this is also IC. And this would mean that this branch is forbidden to take any current or produce any current. This branch is kind of now not present. It's not there, which is not the case. So therefore, that is wrong to do. So we cannot say that we have a same current in the two meshes. Now that we have this one current, this one equation, I have IA times R1 plus IB times R2 equals to 10. This is my first equation, but I need another equation. And the other equation can be seen from the circuit. You see this source current IS, the source current. In this diagram, it is going upwards, okay, which is the same direction as IB. It is the same direction as IB. Now, let me say this and then I will ask you if you agree with that. Let's say, if I say that IB minus IA equals to 3 amperes. Now, this would be my second equation, but the important point here is now to understand if this is the case. So you see the current in this branch where we have a current source, it's 3 amperes. So we know that the current is fixed at 3 amperes, okay? And that current has to go upward, which is the same direction as IB. So whatever IB is, okay, whatever IB is, once I subtract IA from it, it should give me 3 amperes going upward. And that's what I did here. IB minus IA equals to 3. So this gives me the second equation, and I can write it now. Negative IA plus IB equals to 3. So this will be my second equation. And now we have two equations and two unknowns, and we can solve it very easily. I hope you enjoyed this video, and if you did, please consider subscribing to my channel.